the pathway of the blood through the heart. As we've stated, we have in the right side, we have the pulmonary circuit, and in the left side, we have the systemic circulation. So the pulmonary circuit, if you see on here, I'm starting from the right ventricle, passing through the pulmonary trunk and pulmonary semilunar valve to reach the lungs. This is where the oxygenation of the blood going to be taking place. And then this blood going to be drained through the pulmonary veins to my left atrium. Then from the left atrium, I'm passing down to the left ventricle. This is the start of my systemic circuit. I will be pumping this blood, which has been oxygenated in the lungs, into my aorta that will be distributing the blood to all my systemic organs for them to get the oxygen they need for their metabolic activities. The blood that gets drained out of those systemic organs is going to be drained out through veins, and those veins will end up either draining this blood into the superior vena cava or the inferior vena cava. All right, this is for most of the organs, with one exception is going to be the heart itself. The heart itself gets drained by the coronary sinus, as we've mentioned earlier. So right side of the heart, I'm passing from the right atrium, passing through the tricuspid valve to the right ventricle. And then from the right ventricle, I'm passing through the pulmonary semilunar valve to the pulmonary trunk to reach the lungs. Left side of the heart, I'm starting here from the lungs, draining the lung through pulmonary veins to the left atrium. Then from the left atrium, I'm passing through the bicuspid or mitral valve to the left ventricle. Left ventricle will then pump the blood out, passing through the aortic semilunar valve to the aorta, then reach the systemic circulation. Any questions? Any questions? All right, so before we start our discussion of the cardiac muscle physiology, we need first to remember the skeletal muscle contraction. This is very important to remember before we start working on the cardiac muscle contraction. If you remember, back when we studied the nervous system in AP1, we've learned that nerve cells located in the primary motor cortex will create an electrical signal that will travel down through the brain and will pass down to the contralateral side of the body that it controls into the spinal cord. And when it reaches the level that it needs to exit the spinal cord through, it forms a connection with another nerve cell that exits the spinal cord from the ventral horn of the gray matter of the spinal cord. So this is my brain on here, and this will be my spinal cord. Remember, those nerve cells will reach the muscle and causing the muscles to contract in response to this initial electrical signal. If you remember, what allowed the muscle to contract in response to the electrical signal? In order to understand how this did take place, we did magnify the neuromuscular junction. It did have a nerve ending like this, through which the electrical signal is traveling down. If you remember, an electrical signal, when it travels along the plasma membrane of a nerve cell or a muscle cell, it's in the form of a depolarization. If you remember, what's depolarized state? A depolarized state means that the cell membrane has lost its resting membrane polarity. During rest, if you remember, the inside of the cells are more negatively charged compared to the outside, which are more positively charged. So when I have a threshold stimulus, when I get enough excitation, this will cause the stimulation of the nerves and muscles to create their own electrical impulse, their own action potential. So, and the primary phase of the action potential is the depolarization. How this takes place, if you remember, you open sodium channels. So this is my resting membrane polarity. When I get the signal delivered, what am I doing? I open sodium channels. And when I open the sodium channels, what's going to happen? The sodium flows from outside of the cell to the inside of the cell, making the inside of the cell to become more positively charged compared to the outside. So this is my depolarization. I am more positive. So here, this is the type of signal that is traveling along the length of the nerve cell. Positive in, more negative out. This means I'm conducting an electrical signal. This signal did what in the terminal end of the nerve fibers? It did cause the opening of channels for calcium. And if you remember, we call those are my voltage gated calcium channels. Those voltage gated calcium channels will allow the calcium to travel from outside of the nerve cell to the inside of the nerve cell. Why do I need this influx of calcium into my terminal nerve endings? To allow the release of the neurotransmitter stored in its vesicles. So when I allow the calcium in, the vesicles will fuse with the cell membrane, releasing the neurotransmitter, which is going to be located in those cells, is the acetylcholine. So now the acetylcholine is located where? See on here? At the junction between the nerve and the muscle. This is where I've got the acetylcholine released. How this acetylcholine will let your skeletal muscle contract? If you remember, this is the plasma membrane of the muscle cells. This is what we've called the sarcolemma. The acetylcholine binds to its receptors. And as it binds to the receptor, there is associated ion channels to it. This is going to cause the opening of sodium channels. So now the sodium travels into the cells. This is my muscle cell here. Remember, if I don't have a signal traveling along my cytoplasmic membrane, inside is more negatively charged, outside is more positively charged. But what happens when the acetylcholine binds to its receptor? You open sodium channels. Sodium, which is a positively charged ion, gonna travel to the inside of the cell. So now the cell is more positively charged on the inside compared to the outside, which is gonna be more negatively charged. Now I am depolarized. Now I have an electrical signal traveling along my cytoplasmic membrane. This is where, again, this is in my muscle. Remember, parts of the plasma membrane, parts of the sarcolemma are going to be passing to the inside of the cell. And we call those, back in AP1, are my T-tubules. They will allow the electrical signal to travel to the inside of the cell. This is where it gets contact with other calcium channels that when they are opened, they will allow the calcium into the cell. This time it's inside my muscle cell. What is specifically the part that gets excited by this calcium is the smooth endoplasmic reticulum of the skeletal muscle cell. This is what we call the sarcoplasmic reticulum. When I get the calcium from outside to the inside of the endoplasmic reticulum, this causes the endoplasmic reticulum to release calcium out in the cytoplasm. We call this step, it's the calcium-induced calcium release. So I get calcium released into the cytoplasm of the muscle cell due to the influx of another calcium from outside. And again, what allowed the influx of another calcium from outside of the cell is the presence of this electrical signal. And what has created this electrical signal into the muscle cell is the attachment between, again, acetylcholine and its receptor. And where did I get the acetylcholine from again? It was stored inside the terminal endings of the nerve fibers, and an electrical signal coming all the way down from your brain is what caused calcium channels to open in those terminal endings of the nerve fibers, causing the influx of calcium and, as a result, the release of the acetylcholine. Did I have any contraction of the muscle cell so far? No. But this calcium is the one that will allow you to contract your muscles. If you remember, inside the skeletal muscles, we did have two types of myofilaments. We did have thick filaments and thin filaments. Thick filaments are formed of protein subunits called the myosin, compared to the thin filaments are going to be formed of protein subunits called actin. Remember, when the calcium here during rest, the binding sites on the actin subunits are going to be covered with something that we've called the tropomyosin, which is directly attached to another protein subunit called the troponin. The function of the calcium that you've released in here is to bind to the troponin to move away the tropomyosin. And when I move away the tropomyosin, I've exposed the binding site on the actin subunit, allowing the myosin to form a cross bridge to bind, bend, detach, and this allows the sliding of the filaments, causing the shortening in the length of your skeletal muscle cells. All this is a brief review of what we've discussed in details back in AP1, but it's highly essential to understand, it's highly essential to know to make your life easier when we discuss the heart. All right, so please let me know if you have difficulty with any of what we've mentioned so far. Questions? Questions? For those who are still here, please write down that you're present. All right. So no questions, no questions. All right. So we're looking on here at the cardiac muscle. So how is it different from the skeletal muscle contractions that we've just mentioned? First thing that we need to remember is that skeletal muscle contraction was a graded contraction. What I mean by a graded contraction, in a muscle, you have many fibers. It's not essential to contract all of them every time you use a muscle. So for example, if I'm contracting my biceps to flex my forearm, I don't have to use all the muscle fibers inside each time I contract my biceps, right? How many fibers would you be activating? It's gonna be determined according to the load that you're trying to carry. We call this as graded contraction. This is in your skeletal muscles. How about in your heart? All the cardiac muscles are gonna be connected together by gap junctions. So all the muscle cells, all the cardiac muscle cells will be all contracting each time they receive a signal. It's an all or none contraction, whether you contract all the cardiac muscle cells at the same time or you relax them all at the same time. Why again? Due to the presence of gap junctions. What's another major difference here is that your cardiac depolarization is going to be taking place in a rhythmic pattern. For example, your biceps, is there any rhythm for your biceps contractions throughout the day? Do you have to contract 50 times a minute, for example, your biceps? 3 seconds in between each of the contractions? No, there is no regular rhythm for the contraction of the skeletal muscles. On the other hand, my cardiac muscles have a rhythmic and spontaneous contraction. What I mean by spontaneous contraction, I don't rely on an external nerve fiber to deliver the signal for me to initiate the contraction. So here, for the skeletal muscles, where did you get the initial signal? From your brain, right? Here in the heart, I don't need to get an external signal for me to contract. I can contract spontaneously. on my own. I have what I call automaticity. What I mean by automaticity, I am self-excitable. I generate my own electrical impulse. So if you take out the heart, you cut all the nerves connected to it. Will it still be contracting? What do you think? Yes, if you cut every single nerve connected to the heart, it will remain contracting in a rhythmic and spontaneous manner. What allows the heart to contract spontaneously, to have automaticity, is the presence of 1% of the cardiac muscle cells that have the ability to generate electrical impulses. So I have 1% of the cardiac muscle cells that will be self-excitable, that will generate the electrical impulse for all the cardiac muscle cells to contract in response. So what are the members here of the cardiac muscle cells that have automaticity? So if we're looking here at the four chambers of the heart, the first one that we have, it's gonna be located in the right atrium. We call it the sinoatrial node or the SA node. Another one that we have is gonna be also on the right side at the junction between the right atrium and the right ventricle. So it's located between the atrium and the ventricle. So we're gonna call it the atrioventricular node or AV node. The third part of the cardiac muscle cells that can generate their own electrical impulses, it's going to be embedded in the wall of the ventricles. And those tiny fibers embedded in the wall of the ventricles, those are what we call the Purkinje fibers. So again, what are the three different parts of the heart that can generate their own electrical impulses? We've got SA node, AV node, and Purkinje fibers. So why would I have three if I have one that will be sending out the signal to everybody? Why would I have three? This question is what we're going to answer right now. So actually you have three, but each one has a different rate of depolarization. So if we're looking here at the SA node, it can depolarize 75 times per minute. What I mean by this, that you are creating 75 electrical impulses per minute. Compared to the AV node has a slower rate of depolarization compared to the SA node. It can depolarize 50 times per minute. Compared to the Purkinje fibers, they can depolarize only 30 times per minute. So which one would I follow? Would I follow the one that will let me contract 75 times per minute? Would I follow the one that will let me contract 50 times, or the one that will let me contract 30 times per minute? Generally speaking, You follow the fastest node. And normally, which one of the three is the fastest node? Normally, your SA node is the fastest node, exactly as you're saying. Normally, the SA node is the one that has the fastest rate for depolarizations. So what happens to the electrical impulse of the SA node that gets created by the SA node? Remember, all the cardiac muscle cells are connected by gap junctions, so the electrical impulse will travel freely. All right, so the electrical impulse travels freely between the cardiac muscle cells, causing the excitation of all the cardiac muscle cells of both atria. But the only way for me to pass from the atria to the ventricles is by traveling through the AV node. AV node has fewer gap junctions. This will cause a time delay in the transmission of the electrical impulses from the atria towards my ventricles. And this time delay is going to be of a 0.1 second. So getting the electrical impulse traveling between the atria first, and then it will be delayed passing through the AV node to reach my ventricles. This electrical impulse here will travel from my AV node to a bundle located between the atria and the ventricles called the AV bundle. And then this bundle is going to split into a right branch and a left branch. We call those are my right and left bundle branches. That will be reaching the cardiac muscle cells of the ventricles and the Purkinje fibers. Once I get connected to the cardiac muscles of the ventricles, now the ventricles will be able to depolarize starting from the apex upwards. So again, what we're looking at in here, normally my heart is following the SA node. The SA node depolarizes at a rate of 75 times per minute. Electrical impulse can travel from the SA node, which is located in my atria, freely to all the cardiac muscle cells of the atria. So both atria will be depolarized in the same time. But this electrical impulse, in order for it to be conducted towards my ventricles, it needs to travel through my AV node. In order for me to travel through the AV node, there will be some time delay of how long? Of a 0.1 second. After I pass through the AV node, I'm passing down through the AV bundle, then the right and left bundle branches to reach the Purkinje fibers and so cause the excitation of the ventricular cardiac muscle cells. What do you think? Is this time delay something good or bad? To have 0.1 second delay in the electrical conduction moving down from the atria towards the ventricles. Why? What do you think? Is this something good or bad, and why? It's something good. Good, bad, good. But why good? Why is it good? For the atria to not contract in the same time as the ventricles, exactly. So having an electrical signal did do what to the muscle? Remember, when I get the electrical signal in here, what resulted having a depolarization of the muscle? It responds by contracting. So if I did depolarize both atria and ventricles in the same time, what's going to happen? Atria and ventricles will start to contract both in the same time. Is this something good or bad to contract both in the same time? What do you think? It's bad. Why? Because I need to allow the blood to move from the atrium to the ventricle. So what will I need to do? I need to contract the atrium and at the same time to be relaxing the ventricle. If I contract it both in the same time, what's going to happen? The blood will fail to move down from the atrium because definitely the ventricle will create a much greater pressure because I have much more muscles in my ventricles. This will create a much higher pressure, closing the valves, and will prevent the movement of the blood downward due to the atrial contraction. So as if the atria did not contract. All right? If I'm contracting both ventricles and atria in the same time, I will not be moving the blood down from the atria due to the atrial contraction. I will lose some part of the blood that was supposed to move down to my ventricles. So it is something good to have this time delay. This allows what? This allows the atria to receive the signal first. And when I receive the signal first, this means what for me? This means I will contract first. And then I have this delay, and the electrical signal will reach my ventricles. When the electrical signal reaches the ventricles, what's going to happen? The ventricles will respond by contracting. And as they contract, they now can pump this blood out. So why do I have multiple nodes that have automatism? Why I don't just have an SE node to rely on? If I would be normally following the SE node, why would I have an AV node? Why would I have a Purkinje fiber? Backup, exactly. So if a person got a myocardial infarction in here, so this part of the right atrium is dead. So I have malfunctioning SE node. Would my heart stop contracting? What do you think? No. Why? Because simply you're gonna be following the next fastest node. What is the next fastest node that you've got? It's your AV node. What if I did have something called heart block? Signals are not traveling down from the atria to the ventricles. What do you think? Would my heart stop beating? I will move on to follow the next fastest node, which is going to be my Purkinje fibers. Definitely my heart rate will slow down because each time I depolarize, how my heart responds by contracting. So each depolarization is followed by a contraction. Depolarize, you contract. So if I'm telling you that you have the 75 depolarizations per minute on average, this means what in terms of heart rate? That you have contracted your heart how many times? 70 times per minute, 75 times per minute. This is going to be my heart rate. So if a person got a heart block or a malfunctioning SE node, what would you see in terms of heart rate? My heart rate is going to slow down. All right, so what do you think? Do you have any nerve supply to your heart? What do you think? Just a guess. Yes. Why do I need nerves going to my heart? To speed up or slow down? Exactly. To speed up the heart rate or slow it down. I have nerve fibers going to affect the speed of the depolarization of my SE node. Either increase the heart rate or slow down the heart rate by affecting the SE node. So if you're running, you need your heart to contract faster. So what you're going to do, you're going to be activating the sympathetic nervous system. Sympathetic nervous system will send out signals to your SE node by releasing norepinephrine as a neurotransmitter, and this will increase the heart rate. How about if I'm relaxing? What nervous system do you think I would be activating if I'm relaxing? Do I need to increase my heart rate if I'm relaxing? What do you think? Decrease. You need to decrease the heart rate. And which part of the autonomic nervous system is going to be responsible to decrease your heart rate? It's going to be your parasympathetic nervous system. Parasympathetic nervous system is going to be opposing the sympathetic, slowing down my heart rate, reducing the heart rate. Remember, what ion was responsible to allow depolarization was sodium. And which one was responsible for the polarized state? It was my potassium. Remember, sodium is for depolarization and for polarized. All right, so in order for me to polarize, to return to my polarized state, here acetylcholine, which is the neurotransmitter in the parasympathetic nervous system, is gonna open potassium channels. How about the sympathetic that want to get more depolarizations done? It will open instead more sodium channels. All right, so sympathetic, sodium. All right, so this is a good mnemonic here that I've never paid attention to. So sympathetic, SSS, sympathetic is sodium with S. And the one that starts with PP, parasympathetic, it's the one that opens P, also potassium. All right. Questions. So let's have a look on here. You'll notice that this is my parasympathetic nerve fibers. I am sending impulses to both AV node and SA node. Compared to the sympathetic is going to be sending out signals to SA node, AV node, and the Purkinje fibers. Why do you think I don't have a parasympathetic innervation to my Purkinje fibers? See, this is my parasympathetic. It's not giving any innervation to the Purkinje fibers, although it gives innervation to both SE node and AV node. What do you think? Any guesses? Any guesses? Yeah, exactly. So you see on here, if I am relying on the Purkinje fibers, what's going to be my heart rate? See on here, 30 beats per minute. This is too low. There is no way, if you are using Purkinje fibers, to slow it down. 30 beats per minute will barely keep you alive. So there is no need under any condition to slow down Purkinje fibers because they run at a very slow depolarization rate. It's too slow already. You can't slow it down, but can you speed it up? Yes, I can. Actually, I want to speed it up. So I will have, you see on here, sympathetic innervation to the Purkinje fibers. So sympathetic is going to SA node, AV node, Purkinje, compared to parasympathetic is going only to SA node and AV node and not Purkinje fibers. All right, so let's have a look back to the electrical conduction in the heart. So again, this is my right atrium, right ventricle, left atrium, and this is going to be my left ventricle like this. All right, so we've had 2 questions so far in today's meeting. So we're going to start here from question number 3. So please name the marked structures in here. So this will be number 3, 4, both of the branches on here. So it's going to be number 6. and so it's going to be number 7. Yes, question number 2 was what valve does oxygenated blood go through when it leaves the heart? Exactly. Question 2 was the same question as 1, but we changed here deoxygenated to make it oxygenated. Remember? Mentions that this is number 2. This is my SA node, AV node, AV bundle, right and left bundle branches, and those are my Purkinje fibers. No, the recordings are going to be by request, but not going to be posted for everybody. Is this clear, number 5? All right, we can have a break for 10. We come back, discuss more about the heart. Any questions before we go to the break? All right, we'll see you in 10. All right, welcome back. We are now discussing the AKG. If you remember what we've mentioned earlier before break, we stated that the normal pacemaker of the heart, which is the node that the heart will be following normally, is the fastest node, which is the SA node. This is where the depolarization signals will be created. And as it is created much faster than the rest of the heart, it's going to be the ones that's going to be followed by the cardiac muscle cells. So the first thing that gets excited by the depolarization waves emitted from the SA node are going to be the cardiac muscle cells of both atria in the same time. AKG is a graph, a drawing of the electrical changes of the heart. ECG or AKG, it's electrocardiography. Graphy is to draw electricity of the heart. So here we have the different leads that are distributed all over the body, are like cameras that are detecting different voltage changes of the heart. So the first waves that will be drawn by the AKG, it's going to be the depolarization of both atria in the same time. And this is going to be recorded as my P wave. What happens next to this electrical impulse, if you remember? In order for it to reach the ventricles, it did need to travel through the AV node. In order for me to travel through the AV node, there will be some time delay. So there will be no recorded electrical signal during this time delay. Can you remind me how long was this time delay? 0.1 second, exactly. 0.1 second. What happens next? The electrical impulses did reach my ventricular cardiac muscle cells, and both ventricles are going to be depolarized in the same time. So the next recorded complex in here is simply a recording of the ventricular depolarization, and we call this as the QRS complex. What happens after any depolarization? Remember, when I depolarize any cell, the cell returns back to its resting membrane potential. We call this is repolarization. So what happens to the cardiac muscle cells after they depolarize? They will repolarize. So if we look at on here, the ventricles will then repolarize, and this will be recorded on the AKG as my T wave. So again, what are we looking at in here? We're looking at a drawing of the electrical changes that will be taking place in the heart. The first thing that takes place is the depolarization of both atria. This electrical signal is going to be traveling down through the AV node and AV bundle. This will have some time delay, so no electrical impulse is going to be recorded during this latent period. Electrical impulse will then reach my ventricles. So now the ventricular muscle cells are going to be depolarized, and this will be recorded as the QRS complex. So QRS here is showing the ventricular depolarization. What happens after I depolarize? I will repolarize. So repolarization of both ventricles is going to be recorded as my T wave, which is the last wave here recorded. So am I missing something here? What did we say? We have P wave. This is atrial depolarization. QRS complex. This is ventricular depolarization. And finally, T wave, which is ventricular repolarization. Is there anything that is missing here? What do you think? Atrial repolarization. Where is the atrial repolarization exactly? Where is the atrial repolarization? If you notice on here, first I started by atrial depolarization. This is recorded as P wave. Then I have some time delay, no electrical change on the AKG as I'm passing through the AV node. Electrical impulse did reach the cardiac muscles of the ventricles. So now my ventricles are depolarizing, which going to be recorded as the QRS complex. But what is taking place here in my atria? In the same time as the ventricular depolarization is taking place, atrial repolarization is going to be taking place. So why it was not recorded on the AKG? In a very simplified way, which is not correct. Simply the machine will read the higher voltage. What this means? Similar to when you look at the sky. If you look at the sky in the morning, would you see the moon? What do you think? Do you see the moon in the morning? No, right? Very rarely, right? Is it still there? Or it went home in the morning, or it's only working night shift? What do you think? It's still there, right? But why don't we see it? Because of the presence of another source that emits much greater amounts of light in the morning, which is the sun. All right, so this is the same exact concept. So which one do you think going to be emitting much higher voltage? The ventricles with their thick walls or the atria? Which one going to create a higher electrical voltage? Definitely ventricles. So the machine will not see or will neglect the lower voltage, which belongs to the atrial repolarization. That's why atrial repolarization is not going to be recorded on the AKG. So again, what can we see on the AKG? We have P wave, QRS and T. P is marking atrial depolarization. QRS is marking ventricular depolarization. The last wave that is recorded is my T wave, and this marks ventricular repolarization. Why again I don't see an atrial repolarization recorded on the EKG? Simply because it takes place during the same time as my ventricular depolarization. Ventricular depolarization is going to be emitting much higher voltage. So the ventricle, the machine will detect the higher voltage and will neglect the much lower voltage. Does this make sense? All right, so let's have a look at those EKGs. What can I see on here? I see a normal rhythm. I have P, QRS, T. P, QRS, T. P, QRS, T. I have regular pattern. I have regular rhythm, so the same distance between the successive R waves is the same. It's constant. This is the same amount of time between the successive ventricular depolarization. Means I have a regular heart rate, regular rhythm. How about here? What do you think? Is there something wrong with this EKG? Is there anything am I missing here? Long pause. What else? Do you have all the waves that we've mentioned? I'm missing which wave? See on here? I am missing something here. I have QRS T. QRS T. What am I missing? I'm missing my P wave. Missing P wave. Which means what for me? Means what is the significance of the P wave? Can you remind me? It's for atrial depolarization. So atrial depolarization. So I didn't record atrial depolarization, but I've recorded ventricular depolarization followed by ventricular repolarization. So you see on here, what's wrong with this patient? The patient here has a problem with his SA node. So which node is he relying on in this case? If my SA node is not functioning, what is the next fastest node? It's my AV node. AV node was the one that caused the delay of the conduction of the electrical impulse from the atria to the ventricles. Now it is the one that everybody is following. It sends out the electrical signal to atria and ventricles in the same time. Which one would the machine read if I did depolarize both atria and ventricles at the same time? Which one will the machine read? Ventricular depolarization or atrial depolarization? Ventricular. Why? Because I have a much large voltage, much higher voltage. because I have a much larger number of cardiac muscle cells, a much thicker wall as ventricles. And during repolarization, after I'm done with the depolarization, now the ventricles are repolarizing in the same time as atrial repolarization. So now, which one would I be detecting? Atrial re or ventricular repolarization? Which one going to have higher voltage? Definitely my ventricular repolarization. So I will be neglecting all the electrical changes taking place in my atria, because the ventricles and atria are depolarizing and repolarizing both in the same time. So the machine will mainly focus on the greater voltage, which is going to be created by the ventricles and not the atria. What else did you notice on here, on this EKG, that is different from the previous one? If you notice on here, how many big squares do we have in between the successive R waves? This is 1, 2, and 3. 3 big squares, right? What here? 1, 2, 3, 4, 5, almost 6. Almost 6. So this means what? This means that it took me more time for me to create the next signal compared to here. So if it's taking me more time to depolarize, this means I'm able to create more or less depolarizations per minute. What do you think? So if you are producing, let's say, a pen or a pencil, and it takes you now, because of short in supply or whatever reason that you have in the industry, it's gonna take you longer to produce the same pencil. Would you have more or less pencils produced per year if it's gonna take you, let's say, 1 day to produce a pencil rather than 1 hour? So 1 day to produce a pencil, definitely you're gonna end up having much less pencils produced. So here is the same concept. Here I have less beats per minute that will be produced, because I see here a longer duration between the successive beats. This tells me that the heart rate did go down. I have a reduction in my heart rate, and this makes perfect sense. If you remember, what was the rate of depolarization for the SA node and the AV node? SA node was depolarizing on average at a rate of 75 depolarizations per minute, compared to AV node depolarizes at 50 depolarizations per minute. So you see on here, it's much slower compared to the SA node. So you're gonna have a slower heart rate. We call this is junctional rhythm. What I mean by junctional rhythm, because remember, I'm relying on the AV node, which is located at the junction here between the atria and the ventricles. That's why we call it junctional rhythm. How about this one? What do you think? I see P, QRS, T. All right, so QRS, T, then P, then P, QRST, then P, QRST. So what do you notice on here? Not after each P wave, you have QRST. So in some cases, you're going to have a P wave, not followed by QRS. I'm missing QRS. QRST missing. QRST missing. So this means what? This means, see on here, that my atria depolarize each time. So each time I got atrial depolarization. So I got atrial depolarization P, but this didn't pass down to the ventricles. And then nothing recorded here, as nothing did pass to the ventricles. And then SA node fired again, causing another depolarization. This time, the second depolarization was able to travel and cause the depolarization of my ventricles. So I've got another P wave followed by QRST. So what is the problem here? The problem is in the connection between the atria and the ventricles, AV node, AV bundle. Not every time the atria depolarize, there will be ventricular depolarization. This is what we call a heart block. And we have different degrees of heart block. This one that we're looking at on this EKG is the second degree of a regular pattern. Each 2 atrial depolarizations, we've got 1 ventricular depolarization. It's a regular heart block. Each 2 atrial depolarization is going to be followed by 1 ventricular depolarization. So the second degree heart block, which mostly going to be 2-to-1 ratio. Very important. All what we're talking about here is electricity. We didn't mention anything about blood moving yet. Is this clear? Is this clear? So again, what we're talking about in here, we're talking about electricity moving along the plasma membrane of the cells. We didn't mention anything related to blood movement yet. Is this clear? Clear? All right, so we're talking here, depolarization means sodium in, repolarization means potassium out. All right. What can we see on this EKG? Irregular QRSs. So this is a ventricle that decided to contract very fast, creating very rapid QRSs, causing it not to perform an effective ventricular contraction. This is very rapid, shallow contractions resulting from this grossly irregular EKG. All right, it might be due to acute heart attack or electrical shock. All right. This is called ventricular fibrillation. All right, so I will just mention an important concept that we're gonna rely on next discussion when we discuss the cardiac cycle. We're gonna be arranging all what we've learned together. So we've learned that when the muscle depolarizes, it responds by contracting. And remember, what did we mention about the muscle contraction in the heart? That when we do have a contraction in a ventricle or a chamber, whether it's a ventricle or an atrium, there will be a reduction in its volume. And as a result, what's going to happen to the pressure inside? Pressure increases. And as I have an increase in the pressure inside this contracting chamber, what's going to happen? The blood is going to be leaving. It's going to be ejected out of this chamber. So three events on here. First, I have an electrical change. This is taking place on a cellular level. Depolarization. It's going to be followed by contraction of the muscle cells. This is the mechanical change that resulted from the depolarization. After I contract, what happens to my size? I have a reduction in the volume. And when I reduce the volume of a chamber, what's going to happen to the pressure inside? Increase in pressure causing ejection of the blood. So which one takes place first? Depolarization or contraction or blood movement? Which one is first? Depolarization. And when I depolarize, what's going to happen as a result? Contraction. And as I contract, reducing the volume, increasing the pressure, what's going to happen to the blood inside this chamber? Blood gets ejected. Let's see what happens when I repolarize. When I repolarize, what happens to the cardiac muscle cells? When you depolarize, you contract. But when you repolarize, you're going to be doing what to the muscle cells? Relax. And when you relax a chamber, when I relax the chamber, what happens to the volume? Exactly. There will be an increase in my volume. And as there is an increase in the volume, I'm creating what inside? I'm creating vacuum. So what happens to the pressure? Decrease in my pressure. So would the blood move in or out? What do you think? If I have a reduction in the pressure, I'm creating vacuum, I'm creating suction force. So I will be moving blood in. So what's going to happen here? When I relax, the chamber will refill. So three events. You start by electrical change, followed by mechanical movement that caused a blood movement. So I did repolarize, and when I repolarize, I relax to refill. So if I have a very, very rapid cardiac contraction, is this something good? Will it always supply good amounts of blood? If I have very rapid heart rate, something like this, was this be something good? No. Why? Because if you don't repolarize, you don't relax, and you will not refill. And if you don't refill the chambers with blood, you have nothing to pump on the next beat. If you kept beating so fast, you don't get a chance to fill the chamber with blood for you to eject when you contract again. Because where do you get the blood that you're ejecting from? From the relaxation phase.